Hi, hello viewers. Hope you are enjoying my educational videos. Now I am today going to discuss LR circuit, the growth and decay of current in LR circuit, okay, and few other things. So let's see. Mutual inductance of a solenoid surrounded by a coil, and then I will discuss combination of inductances, the two types of combination, series and parallel combination, and third, the growth and decay of current in LR circuit. So let us start. Mutual inductance of a solenoid surrounded by a coil. Let us draw the picture first. Now in this figure there are two coils. Okay, this R1, this coil has radius R1 and its length is L1. Okay, and it has N1 number of turns, and this coil of radius R2 has N2 number of turns, and it is surrounding this coil R1. Now to calculate the mutual inductance between these two coil of radius R1 and R2, we assume that a current I1 is flowing in this coil. Okay, so here is current I1 is flowing through this coil. Now due to this current, the magnetic field along the axis of the solenoid is this B equals to this value of the magnetic field in the axis of the solenoid. Okay, through this solenoid, this magnetic field. Now this is the magnetic field also inside this coil of radius R2, right, and this field is directed parallel to the axis of the coil. So the magnetic flux phi B2 surrounding the coil is, what is the magnetic field B times the cross section pi R1 square. Okay, and this is the flux flowing through this coil R2 also, because the field will only remain inside this solenoid, so this will be the magnetic flux. Clear? This is the magnetic flux inside the coil of radius R2. So phi B2 is B into pi R1 square. You may surprise that why this is pi R1 square, because this is the cross section through which we are calculating this flux B dot S, right? So mu 0 N1 I1 by L1 into pi R1 square. Now the mutual inductance M is N2 phi B2 by I1. From definition we get. Now we replace this phi B2 by this term. Okay, mu 0 N1 I1 by L1 into pi R1 square. So we get N2 by I1 into mu 0 N1 I1 by L1 times pi R square, and after simplifying we get mu 0 N1 into pi R1 square by L1. So the final expression for this mutual inductance M is mu 0 N1 into by L1 into pi R1 square. So there is no term regarding R2, right? This is we have to keep in mind. And this mutual inductance is independent of this secondary coil, radius of the secondary coil, because the magnetic field is only confined into this solenoid of radius R1 in this region. So it is irrespective to use this radius here in mutual inductance. Now we can also calculate the mutual inductance by calculating this current through current is flowing through these R2 radius, and we will get and the same expression, because we know the M12, because we know M12 is equals to M21, but for the later case M12 is equals to M21, M21, because so this M21 part, if we calculate this is a very complex calculation, so we'll leave this calculation. We just going for a simple calculation and easy calculation to find the mutual inductance. So this is the final expression. So it depends on only on the dimension of the two coils, the number of turns of the secondary coil N2, and the rest of the terms all included in the primary coil R1, right? Now we are going to calculate combination of inductances. First we will calculate the series combination. That is our working diagram. We have first taken 3 inductor L1, L2 and L3. Now, so in each inductor there is a voltage drop. So the first the voltage drop through inductor L1 is equals to VAC, and we write this VA minus VC equals to L1 di dt. Di dt is the change in current through this inductor, right? Now the same voltage drop VCD, but VCD is equals to L2 into di dt, and again we get the voltage drop VDB, right? VD minus VB equals to L3 di dt. Now the total, we sum up all these quantities, then this VC cancel out, this VD cancel out, only remaining part is VA minus VB. So VA minus VB is equals to the sum of the inductors L1 plus L2 plus L3 and di dt, right? Now we have taken the equivalent inductance as L, right? So the voltage drop across this equivalent inductor VAB is VA minus VB equals to L di dt. Okay. Now we compare these two equations, this equation and these two equations. So what we get, L di dt equals to L1 plus L2 plus L3 and di dt. So after comparing we get the equivalent inductance L equals to L1 plus L2 plus L3. This is taken for 3 inductors. If there are n number of inductors, it is simply sum of the inductors L1 plus L2 plus dot dot Ln, right? So this is the series combination of the inductances. Now we will find the parallel combination. That is our working diagram. So in series case we have seen the voltages were added. Now this current through this parallel combination, in each part of this circuit the current is divided. Let's say in first inductor current is I1, in second inductor current is I2, and in third inductor current is I3, right? So we write total current I is equals to, what we get, total current I equals to I1 plus I2 plus I3. This current is flowing through the 3 branches and again meeting up there and making I. So we get here time derivative of this current, or the rate of change of current, di dt is equals to di1 dt, di2 dt, di3 dt. So this individual changes across the inductors, total change. Now this di1 dt is the VA minus VB by L. Why? Because we get VA minus VB is 1 L di dt. We are using this formula, so we get VA minus VB because we find the EMF E equals to L di and dt. Okay, this is di and dt. So as it is E is the voltage drop. Okay, so we replace this di1 by dt is VA minus VB by L1. Similarly for di to dt we replace this VA minus VB by L2, and for di3 dt we get VA minus VB by L3. So the potential drop is the same across these 3 inductors, right? So their equivalent inductance is here di dt. So what we get, their equivalent inductance di dt is equals to VA minus VB by L, and we get, after comparing these two equations, what we get, 1 by L equals to 1 by L1 plus 1 by L2 plus 1 by L3. This is the equivalent inductance for parallel combination. So for parallel combination we get this. If there are n number of inductors, then we will get 1 by L, the equivalent inductance equals to 1 by L1 plus 1 by L2 plus 1 by L3 plus dot dot 1 by Ln. Okay, so these are the combination of inductances in circuits. Now we will find the growth and decay of current in LR circuit. So we are going to detailed study of LR circuit. First, the diagram. We explain this diagram. There is a voltage source E1 and a switch S1 and another switch S2 for decay. Now there is another circuit component and represent the resistance as R, and there is an inductor. So this is the simple form of a LR circuit. So what we will find here, that there is a voltage drop across R, okay, and also there is a voltage drop across L. So we first write down the KVL for this circuit. Okay, now when we close this circuit, a current flows through this circuit and we are going to write the KVL. So this is the KVL. E minus VA minus VB minus VBC equals to 0. So now VAB is the voltage drop. What we call is VR is that I in times R. So this voltage drop is I times R. Okay, and this voltage drop is L di dt. This is L di dt. Okay, so this is the KVL for this equation. Now we will rearrange this equation as to find. Okay, we are going to rearrange this equation. Okay, this is the equation. L d I dt equals to L di dt equals to E minus IR. E minus IR. Then we will find what? L by dt equals to E minus IR by di. E minus IR by di. Okay, now after rearranging this, we will write this equation. 0 to I. Okay, we just erase all the ink. We find this integration 0 to I di by E minus IR equals to integration 0 to t dt by L. Now when we switch S1 is closed, the current start flowing in the circuit, and this current has reached I at time t. Okay, so we have taken the integration limit. Now we will integrate this equation. This integration will be given in comment section. Now the final value of this integration is I equals to E by R and 1 minus e to the power minus RT by L. Okay, and we further simplify it as I equals to I0. We are putting E by R as I0. So we are putting I0 equals to E by R, right? And 1 minus e to the power minus t by tau L, and this tau L is R by L. Now further we will clarify this tau L in the next slide. So we get the growth of current I equals to I0 1 minus e to the power minus t by tau L, right? Now we see the graph, IT graph, the current time graph. This is the current time graph. Okay, here is the time axis and this is the current axis. The maximum current I0 equals to E by R, right? Now a new term, the tau L, it is called time constant. So why? This tau L is the inductance by the resistance of the circuit. So first find the dimension of inductance is m L square to the power minus 2 I to the power minus 2, and dimension of resistance m L square to the power minus 3 I to the power minus 2. When we find this dimension L by R, we get the dimension of a time, and this tau L is a time. Now this equation, we have plotted this equation here, and we get what? When t equals to tau L, what we find? I equals to I0 1 minus 1 by E. Now 1 minus 1 by E is 0.63. So we can say that when time reaches tau L, we get the current in the circuit as 63% of its final value. This is the time constant. Okay. This is very important in this graph, in growth of current. Now we will study decay of current in LR circuit. So there is no need of battery. We just off the battery and get this simplified circuit. So there is a voltage drop across R and there is a voltage drop across L. So who will supply current? This inductor will supply this current, right? So inductor will supply this current. So voltage equation in this circuit is VA minus VB plus VB minus VC equals to 0, as there is no external source added to this circuit, because we are studying the decay of current. And VA minus VB is simply IR, and VB minus VC is the voltage drop across the inductor L di dt. Now further simplifying, di by I equals to minus R by L into dt, and again integrate. So what is, at first it is when battery is disconnected, it has the maximum current I0, right? So when the decay starts, the current was I0 when the decay starts. Now at time t, I say the current is I. Okay, we are considering this situation as the integral limit. So we get this I0 to I di by I equals to minus R by L integration 0 to t dt. After integrate, we get I equals to I0 e to the power minus t by tau L. Now we study the graph here. Here again we find the time constant tau L equals to L by R, and this is the graph. This graph is for I equals to I0 e to the power minus t by tau L. So this is the maximum value of the current I0, and after as time goes, it comes at tau L 37% of its initial value, right? So this is time constant for decay of current through LR circuit, right? And at tau 1 TL we get I equals to 0.37 I0. So time constant is that time when the current in the circuit is 37% of its initial current I0. So hope you enjoyed this video, and thank you.